Take a look at this glowing magenta line on the flight display. It represents a perfect straight path connecting a departure city to a destination. Drawing that line on a screen takes a fraction of a second. Actually, flying it requires overcoming multiple layers of planetary physics. Every flight is governed by a mathematical relationship known as the triangle of velocities. A pilot must balance the aircraft's heading and its true airspeed against the specific direction and speed of the wind to achieve their desired track across the ground. Setting up that geometric triangle is impossible without first mathematically correcting the physical shape of the Earth itself. Executing that triangle in the air is equally impossible without correcting for the mechanical flaws of physical compasses and the atmospheric distortion of radio waves. Modern navigation relies on a continuous, step-by-step mathematical triumph over three natural flaws of our planet. We start by looking at this image of Earth, establishing our baseline environment. The planet is not a perfect sphere. It is an oblate spheroid, compressed at the poles and bulging at the equator, spinning on a 23.5-degree axial tilt. Because the Earth is curved, lines of longitude, meridians, are not parallel. They are widest apart at the equator and steadily converge until they meet at the true geographic poles. This creates a plotting problem. The absolute shortest physical distance between any 2 points on a sphere is a great circle. But as a great circle crosses those converging meridians, its relative angle constantly changes. In this 3D model, you can see the great circle curving relative to the grid. Below it is a rhumb line. A rhumb line cuts across every converging meridian at the exact same angle. This allows a pilot to fly a constant, easy-to-steer heading, but it results in a physically longer overall flight path. The angular difference between the great circle path and the rhumb line is called the conversion angle, which is mathematically equal to exactly 1/2 of the Earth's convergency at that latitude. Aviation solves this plotting geometry using the Lambert conformal conic chart. We mathematically place a cone over the Earth so that it cuts through the surface at 2 specific latitudes, known as the standard parallels. Unrolling this cone into a flat projection creates a map where our highly efficient great circles plot as practically straight lines. However, the physical scale of the map is only 100% accurate exactly along those 2 standard parallels. To merely draw our intended flight path, we systematically distort our maps to account for the physical curvature of the planet. Once the line is drawn, a pilot needs a pointer to navigate it. True north is a geographic absolute, anchored at the poles, but magnetic north shifts. The angular difference between geographic true north and magnetic north is called variation. Inside the aircraft, this physical magnetic compass introduces a second error. The metallic structure of the aircraft itself creates a localized magnetic field, pulling the needle away from magnetic north. This structural error is called deviation. Navigators resolve these static errors sequentially. Compass heading plus deviation equals the magnetic heading. Add the local variation, and you find your true geographic heading. Look at this cross-section of the Earth's magnetic field. This highlights a dynamic, fatal flaw in navigation. Magnetic flux lines run horizontally at the equator, but moving toward the poles, a vertical downward force, known as dip, pulls the flux lines straight into the ground. To prevent the compass needle from pointing down at the floor, engineers use pendulous suspension. They add a heavy weight low below the pivot point, using gravity to counter that downward magnetic pull and keep the compass card level. That heavy pendulum makes the instrument highly vulnerable to kinetic forces. When an aircraft accelerates on an east or west heading, the physical inertia tilts the pendulum backward. The compass card rotates, registering a completely false turn toward the north. Decelerate, and it registers a false turn to the south. Banked turns trigger a different physical lie. When turning through north, the compass card sluggishly underreads the turn. When rolling through south, it wildly overreads the turn, racing ahead of the aircraft's actual nose. To compound the problem, the liquid surrounding the compass card gains momentum during a turn. This liquid swirl physically drags the card further out of alignment. Relying on the Earth's magnetic field forces pilots to use pendulous instruments that physically lie every time they change speed or alter bank angle. Once pointed on a heading, the fluid atmosphere asserts itself. Wind physically pushes the aircraft off its intended path,
requiring constant dead-reckoning navigation. Pilots manage this drift using the 1 in 60 rule, a mental geometry shortcut. By calculating their track error angle against their closing angle, they determine the exact degree of heading correction required to regain their line. This dead-reckoning math dictates hard survival limits, the critical point, where an engine failure demands exactly equal time to proceed or return, and the point of no return, the absolute maximum distance the aircraft can fly based on its fuel endurance. To verify their dead-reckoned position, aircraft use an automatic direction finder to track ground-based non-directional beacons. A basic loop aerial receives the radio signal in a figure-8 pattern, which tells the pilot the line of the station, but creates a dangerous 180-degree ambiguity on whether it is ahead or behind them. By electrically combining that figure-8 loop pattern with a circular sense aerial, this diagram shows how the system generates a single heart-shaped cardioid wave. This cardioid contains exactly one sharp null point, allowing the instrument to definitively point at the station. But external radio waves are highly vulnerable to the environment. Coastal refraction occurs because radio waves physically speed up and bend as they pass from dense landmasses over less dense open water, throwing off the bearing. At night, ionospheric sky wave bounce causes the signal to fade and wander. Furthermore, thunderstorms emit massive amounts of low-frequency energy. Fly near a storm, and the radio needle will abandon the navigation beacon and point straight into the lightning. Ground-based radio eliminates mechanical flaws of a compass, but its signals are too easily corrupted by the planet's atmosphere to serve as an absolute solution. To achieve true precision, aerospace engineering required a completely self-contained system, one that ignores magnetic fields, radio waves, and takes zero inputs from the outside environment. The solution is the inertial navigation system. Instead of looking outside, it uses internal accelerometers mounted on a gyro-stabilized platform to measure physical movement along the north-south and east-west axes. The onboard computer integrates that acceleration data over time to determine velocity. It then integrates that velocity over time to determine the exact distance flown and the precise geographic position. The system has one initial flaw. Tiny gravity measurement errors by the accelerometers will rapidly compound, accumulating infinitely over the duration of a long flight. This diagram illustrates the mathematical fix known as Schuler tuning. Engineers tuned the system to behave exactly like a pendulum spanning the Earth's radius, swinging in an 84.4-minute arc. This traps the gravity error in a bounded oscillation, preventing it from compounding. The modern evolution of this concept is the ring laser gyroscope. It replaces mechanical spinning metal with trapped light. Inside an optical cavity, two laser beams travel in opposite directions around a sealed triangle. When the aircraft rotates even a fraction of a degree, the path length for one beam slightly increases while the other decreases. The laser waves shift out of phase, creating an interference fringe pattern that measures movement with extreme microscopic precision. At very low rotation speeds, the frequencies of the two lasers try to lock together. To prevent this, a mechanical dither motor rapidly vibrates the sensor block, forcing the lasers to remain independent. Utilizing pure inertia and the quantum physics of laser light, aviation finally achieved a navigation system entirely immune to planetary geometry, magnetic dip, and atmospheric weather. Safe flight is a constant mathematical battle against the physical reality of the planet. The industry bypassed the oblate geometry of the globe, engineered its way out of pendulous compass errors, and abandoned refracted radio waves entirely. The final flawless track is achieved by perfectly layering the geometry of the Lambert conformal chart, the continuous calculation of the wind vector triangle, and the closed-loop precision of the ring laser gyroscope. By completely mastering the triangle of velocities, engineering guarantees a precise outcome. The theoretical line drawn on the chart matches the exact physical path flown.